মানে সেমিনারটা আলাদা দিক 3 দিন নাকি রোগী আসে না স্টার্ট আপ সেইটারই গুগল মিট ডাউন হয়েছে
তো ওই গুগল মিটে ভিডিওটা অন করে দেবে তাহলে ওইটা গুগল মিটটা অন করো ওটা ভিডিওটা অন করে দেবে বুঝলে এটা ভিডিওটা অন করে বুঝতে হয় আর এটা আইডিপিটা অন করো
আমি ফর্মটা দিতে পারি তারা মেম্বার হতে পারে ফর্ম আছে আমাদের ও আচ্ছা
জায়গাটা চার্জ এখন জায়গাটা বসে গেল নাকি অ্যাড করে দেবে যদি কিছু অটোমেটিক
এবার এখানে তো
চিনতে পারছি
ও আইডিবির জন্য কি করতে হবে স্যার
ও আইডিপির জন্য কে শেয়ার করতে আইডিপিটা অফ আছে তো শুনি অন করে
এটা
ওর ওই কে শেয়ারটাকে অন করে দিলি অটোমেটিক্যালি
হ্যাঁ পাওয়ার দেয়
কে শেয়ার এখানে স্যার এখানে আসলাম কি Let's start it.
Good morning, everyone. I welcome you all in this occasion organized by Department of Physics. I'd like to invite Dr. Deepti Banerjee to come on stage and deliver her welcome speech. Good morning, everyone, and very warm welcome to all of you. It is wonderful to see so many familiar faces gathered to reconnect and reminisce. This is day is special as we will be mesmerized by the delighted lectures of our post ex-students from online and offline mode from India and abroad. We have a rich past to look back on and a diverse and bright future to look forward to. The energy gain of students have been increased in multiple. We are eagerly waiting to learn and realize their growth and depth in their field of research. Apart from academic vibration, we will also oscillate in the musical atmosphere created by past and present students. We are very happy by the response of the participants and hope the show will go on every year. Now, I will not speak much because it will be wastage of time. So before concluding, I like to welcome our chief guest, Dr. Monisha Bhattacharya on the stage. Please come, ma'am. Please. I request students to offer our auditorium. We also request our special guest, Dr. Krishna Bora, to come up on the stage. And student, please welcome her with flowers and.
Thank you.
Now we welcome our principal of this esteemed institution, Dr. Sutaparai, to come on the stage. Student, please welcome her with flowers and.
আচ্ছা শুনুন আমি তো সেমিনারে যদি পরে করবো সন্ধ্যে থেকে করে
Now we request our uh, first year same one student, Trishita Maiti, to come on the stage and sing the opening song. And after the opening song, we request our principal ma'am to have the inaugural speech. Okay, thank you. Please enjoy the event.
জগত জুড়ে উদার সুরে আনন্দ গান বাজে। জগত জুড়ে উদার সুরে আনন্দ গান বাজে। বিরাট করে গভীর রবে বাজিবে হিয়া বাজে। জগত জুড়ে উদার সুরে আনন্দ গান বাজে। বাতাস জল আকাশ সোনারি কবে বাসিব ভার হৃদয় শোভা জুড়িয়া তারা বসিবে আমার সাজে। বাতাস জল আকাশ সময় কবে বাসিব ভার হৃদয় শোভা জুড়িয়া তারা বসিবে আমার সাজে। জগত জুড়ে উদার সুরে আনন্দ গান বাজে। নয়ন দুটি মিলিলে কবে পরাণ হবে খুশি। যে পথ দিয়া চলিয়া যাব সবারে যাব তোষি। রয়েছ তুমি এ কথা বলে জীবন মাঝে সফল হবে। রয়েছ তুমি এ কথা বলে জীবন মাঝে সহজ হবে। আপনি কবে তোমারি নাম ধরিবে সব কাজে। জগত জুড়ে উদার সুরে আনন্দ গান বাজে। ডাইসে উপস্থিত মনীষা ম্যাডাম আর কৃষ্ণা ম্যাডামকে আমার বিকাশ আর হলে এখানে উপস্থিত সকলকে এই অভিনন্দন জানাচ্ছি। আজকের এই হল দেখে একটা কথা আমার মনে হলো, ছোট পরিবার সুখী পরিবার। কাজে সবসময় অ্যাবসেন্স কে যে নেগেটিভ ভাবে দেখা মানে উচিত সেটা নয়। তবে ডেফিনেটলি উই উড বি মোর হ্যাপি ইফ পার্টিসিপেন্টস উড হ্যাভ বিন গ্রেটার। তবে ইভেন্টস তো অনেক হয় কলেজের। আজকের এই ইভেন্টটা এই জন্য ডিফারেন্ট, ইউনিক অ্যান্ড ইনোভেটিভ বিকজ দিস ইজ ফার্স্ট টাইম যে একটা ডিপার্টমেন্টের তরফ থেকে একটা রিউনিয়ন করা হচ্ছে। আমি রাইট অর রং? আগে তো নিশ্চয়ই কোনো ডিপার্টমেন্ট এইভাবে করেনি। ম্যাডাম দীপ্তি ম্যাডামের প্রচেষ্টাকে আর বাকি যারা ওনার সাথে আছেন ডিপার্টমেন্টে, উদয় স্যার, সুমন স্যার, শ্যামল স্যার, সবাইকে সাধুবাদ জানাই এই প্রচেষ্টার জন্য। আর একটা দিক খুলে দিল, আমি চাইবো যে আজকের এই প্রচেষ্টাটা স্প্রেড করুক অন্যান্য ডিপার্টমেন্টের মধ্যেও, যাতে তারাও এই ধরনের ইউনিয়ন করতে মানে আগ্রহ এগিয়ে আসে। টুডে ইজ আ ব্রিজ, টুডে ইজ আ ব্রিজ বিটুইন দ্য পাস্ট অ্যান্ড দ্য ফিউচার। আপনারা আগে ছিলেন কলেজের সাথে যুক্ত, আজকে আপনাদেরকে কলেজে ফিরে আসতে দেখে সত্যি খুব ভালো লাগছে। একটা কথা আমার হচ্ছে যে we always feel yesterday is a dream and tomorrow a future. But today, well spent, makes every yesterday a dream of happiness and the future a future of hope. So, today is a very important day for the Department of Physics. I appreciate and congratulate the department for having organized this kind of a program. And of course, the students who are all enthusiastic over here. I love the way she said that, can I hug you? So, emotions are the most important part of our life. Whatever we do, we should always do it with sincerity, with emotion, so that, it gives a sense of fulfillment. So I am sure Vidyasagar will have this sense of fulfillment. Today I am here. অনেকটাই ওনার জন্য I have a very important assignment from which I was thinking of taking a leave. But ম্যাডাম যখন এসে বললেন যে এটা হবে তাহলে আপনি থাকবেন তো ম্যাডাম, আমি না করতে পারিনি। থ্যাংক ইউ ম্যাডাম। যার জন্যে না ম্যাডাম আপনাদের সত্যি মানে মেয়েদের অভাব ঠিকই, কিন্তু আপনাদের তো দেখেছি আপনাদের চেষ্টার কোনো ত্রুটি নেই। আর আপনারা যারা আগে ছিলেন কলেজে তারা আরো আসবেন, যুক্ত থাকবেন। আমার তরফ থেকে এটাই আমি আপনাদের বলবো, আপনাদেরও ভালো লাগবে। কাম এন্ড কন্ট্রিবিউট টু দ্য ইনস্টিটিউশন। জাস্ট বিকজ একটা এজ ডায়মন্ড হয়ে গেল মানেই টুডে ইউ আর নোবডি। আমি যেটা সবসময় বলি যে বিসিএফডব্লিউ ফ্যামিলিতে ঢোকার যেরকম মানে আপনারা ঢুকেছেন, স্টুডেন্ট হোক কি বলে টিচার্স হোক, সেরকম বেরোনোর কিন্তু কোনো রাস্তা নেই। তাই জন্য টিল দ্য লাস্ট ডে ইউ আর আ পার্ট অফ দ্য বিসিএফডব্লিউ ফ্যামিলি। হ্যাঁ, লিখে এনেছিলাম অনেক কিছু বলার জন্য, বাট সেটা আমি বলছি না। তবে হ্যাঁ, রবি ঠাকুরের একটা লাইন আমার মনে হয়েছিল যে আজকে এটা বলি, যে আলো নিজের মধ্যে জ্বালাতে পারে সেই আলো অন্যকে দিতে পারে। সো লেট আস devote this day today to I mean trying to enlighten this light within us. আর আজকে যারা বলছেন সবাই কি এসে গেছেন ম্যাডাম? যারা আজকে বলবেন তারা সবাই দুজন অনলাইন, দুজন অফলাইন। দুজন অনলাইন, দুজন অফলাইন। ডক্টর অনন্যা মুখার্জি, do I don't know? Just অনন্যা, sorry, offline,
অন্তরা
আর আজমিরা। আচ্ছা, অনিন্দিতা কর্মকার এসেছেন
অনলাইন
অনলাইন থেকে। আচ্ছা, ওকে ওকে। ডক্টর অন্তরা দে,
অলরেডি জয়েন করছি।
আচ্ছা ওকে ওকে, ভেরি গুড। হ্যাঁ, এখানে তো বোধহয় দেখতে হবে না, অনিন্দিতা ইজ দেয়ার, রাইট? Acha. And Ajmira, you are Ajmira. Okay, welcome, welcome, welcome to all of you. Back to your roots. So, আজকে তোমরা যে জায়গায় আছো, I was very impressed while reading your, short bio note, right? So, আর আছেন রাইমা সাহা, উনিও বোধহয় অনলাইনে নাকি?
অফলাইনে ছিল, আসতে পারবে না।
Oh, আচ্ছা। Anyway, welcome to all of you. Today, wherever you are, যেটা বলতে চাইছিলাম, it's because of your teachers. And I will want that you come back and give back to the institution whatever little bit. And for that you have come. I thank you very much. And this should continue. যেটা দীপ্তি ম্যাডামও বললেন, I also want that এটা আজকে শুরু হলো, তাই জন্যই এই প্রোগ্রামটা এত ইম্পর্টেন্ট, যে একটা দিক দেখাচ্ছে তো, যে হ্যাঁ একটা ডিপার্টমেন্ট তো তাদের অ্যালুমনাই, আপনারা অ্যালুমনাই অ্যাসোসিয়েশন একটা ফর্ম করুন ডিপার্টমেন্টাল লেভেলে, সো দ্যাট ব্যাপারটা অনেক অর্গানাইজড হয়ে যায়। And I wish this event all the success. Thank you very much. Thank you very
পরিবেশটা কোথায় গেল? এই অনিমেষ থেকে ফোকাস করুন।
তুই নিচে দাঁড়িয়ে থাক, লাইন যদি আসে আমাকে জানাবি ফোন করে। হ্যাঁ হ্যাঁ,
এইটা কি?
আমরাও ক্লিয়ার।
আমি ট্রাই করে গেলাম। এত নাকি সাফোকেশন হচ্ছে।
কেক কাটার জন্য সকলকে স্টেজে আসার জন্য অনুরোধ করা হচ্ছে। স্টুডেন্টরা সবাই এসো।
অসিত আসুন।
এসো এসো। তোমার এখনই বলতে বারোটা থেকে বলেছি। ঠিক আছে, সব ভালো।
আমি এলাম ম্যাডাম, আপনি
সুমন এসো।
সবাই চলে আসুন।
না ওটা দিয়ে যে দেখাতে হয় তাহলে কি ওই টাইম করে দেবো?
না, আজকে ডিপার্টমেন্টে ছিল তো। আপনারা ধরবেন
সুমন দা চলে এসো। এই সবাই ধরো।
Happy birthday. একটা খুব সুন্দর প্ল্যান করেছে। না, আমার মনে হয় এটা ডিভাইড করছে সবার না হাতে এটাই অসুবিধা হয়।
মনীষাদিকে দিয়ে দিই কেন, বিকজ মনীষাদির ব্যাপারটা আমার কেন বলছি, আমি সাকুয়াতে 11-12 মনীষাদির টিচার। তারপরে আমি যখন আইএসআইতে রিসার্চ করি ফুল ফ্লেজেড, তখন মনীষাদি এখান থেকে ওখানে পার্ট টাইম রিসার্চ করতে যেতেন, তখন আমার একটু আড্ডা। তারপরে যখন ঘুরে ফিরে এই কলেজে এসে জয়েন করি, আমি মনীষাদির পোস্টেই জয়েন করছি। টিচার আমি ঠাকুরের কাছে বলবো আমার পোস্টে আমার স্টুডেন্টরা এসে জয়েন করবে, এটাই আমার ভাবনা।
এই তো সবাই
এটাই আমার ভাবনা। মানে ভালো স্টুডেন্ট আছে তারা যেন আসে, আমি তখন খুব শান্তি পাবো।
ম্যাডাম কি দেওয়া? ম্যাডাম আপনাকে
আলাদা আপনি শান্তি
উনিও সেটা তো নামিয়ে দাও।
টিস্যু আছে দেখছি তো না।
টিস্যু আনতে গেছে। খানিকটা হয়ে গেল ম্যাডাম একটা ভালো করেছে না
তারপরে হচ্ছে
patience. কিছু হবে না, কিছু হবে না। এখানে একটা
এরকম করে একটা করে দিন যায় admit করে দাও তো admit দাও অনলাইনে দাও অনলাইনে দাও
লাইন
আমাদের ব্রেন
Spotlight, spotlight.
এখানটা রাখতে পারবো স্যার?
হ্যাঁ হ্যাঁ কি হলো হ্যাঁ শর্ট কোট কিন্তু অনেকে যখন প্রেজেন্ট করবে তো প্রেজেন্টেশন গুলো দেখা যায় হ্যাঁ সেটা করতে হয় তখন দুটো দুটো প্রিন্ট করতে হয় না এইটা তো ইউটিউব
Now, our technical session is going to start. Our first speaker is Dr. Anindita Kormokar, our ex-student of a batch 2017. She passed BSc Physics Honors in the year 2017, obviously with first class. And she did her MSc from IIT Roorkee and completed it is on 2019. And after that, same year, she joined in the Shaha Institute of Nuclear Physics, SINP, Salt Lake, for doing PhD. And she finished PhD in this year. And now she is doing postdoc, started postdoc in the Tata Institute of Fundamental Research, Mumbai, as postdoctoral research. In this point, I am taking the privilege to mention that our teacher, Dr. Uday Pramani, is also did his postdoc there in the TIFR. And after, from TIFR, he joined in this college. Dr. Kormokar is an experimental nuclear physicist specializing in nuclear structure and gamma ray spectroscopy. She is currently involved in detector testing and development of new beamline. Now, her title of the talk is Nuclear Physics from a Beginner's Perspective. Welcome,
Hello.
Anindita, and
Good
start
morning.
your talk.
Yeah, am I audible to everyone?
Mute হয়ে গেছে।
এই যে ওটা ভলিউমটা বাড়াবো। হ্যাঁ 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 ওই জায়গা প্লাস্টিক দাও।
Oh, am I audible? Oh, it's echoing. Okay. I will share my screen. Mm, Okay, just a moment. Okay, just a moment. Mm, Okay. Is my screen visible? Oh, sorry. Okay. So is my screen visible? Oh, okay. So, good morning, everyone. I am Anindita Kormakar, and also thank you, ma'am, for this very nice introduction. And I'm privileged to be part of this endeavor that you are all pursuing for a very long time and meticulous planning and everything. And I'm really honored to be the first speaker of the session. So the title of my presentation is Nuclear Physics from Beginner's Perspective, and I really made the slides focused on the students so that I can make them understand that what exactly my work is. And like ma'am said, I finished my PhD very recently in 2024, and currently what work I did in my PhD was mostly analysis based, but currently now I am part of the instrumentation also. So I would like to just give a brief overview of what I have been doing or what I have done so far. So if the students are there, I mean, the teachers are all very much well aware of what is this, but if the students are there, so how do we see the elements? So the elements are mostly categorized based on their atomic numbers. So hydrogen, helium, 1, 2, 3, 4, and depending on that. But problem is that each element that we see in our nature has various isotopes. Like for example, there is chlorine, and chlorine has 35 chlorine and 37 chlorine, both the isotopes. So when you are talking about natural chlorine, so natural chlorine has both the isotopes present in it, and the percentage of isotopes that are present in a element, that is called the abundance, natural abundance of an element. So chlorine has of natural abundance where both 35 chlorine and 37 chlorine are present. But when we are talking about the periodic table, you see that there is no other thing that you can watch here, because there's no other isotopes are visible in this nuclear chart. So that is the only flaw of the periodic table, but it is categorized very well. And that is how normal people see nuclei. But how nuclear physicists see the elements is that there is n in y x-axis and z in y-axis, and all the elements of all the isotopes are present in this chart, and this is called a Segre chart. So what is the specialty and what is the main difference, key difference between a periodic table and a Segre chart is that periodic table only involves the atomic number and judge their chemical properties. But in Segre chart, you can also see the neutron number and proton number and all the isotopes of all the elements that are present. Suppose that in the lower neutron region, where n is almost equal to 28, these nucleons are in almost equal to Z nuclei. So as the number of neutron or proton increases, the neutron numbers are more compared to the proton numbers. Because as the number of proton increases, the repulsion between all these protons increases more and more. And so to bind them, we need more number of neutrons. That is why, as the Z increases, the stability line, as you can see here, increases, and the slope is more towards the N, uh, more towards the N. So this is central line. This is called the stable nuclei. The stable nuclei is what? Where the ground state lifetimes are 0 and it does not decay to other elements. And what are unstable nuclei? Unstable nuclei are those nuclei where the ground state transition has a finite lifetime, say in the order of nanosecond or picosecond or sometimes microsecond days. But it just emits radiation like alpha, beta. This kind of radiation happens and it decays to a more stable version of nuclei. So this happens in more like this proton-rich or neutron-rich nuclei. And there are also prolates, oblates, various kind of shapes. I will be more coming to the shapes later. So first of all, I hope everybody, every student currently understand what is the difference between periodic table and the shape data. Okay. So, so when I'm talking about nuclei, we treat nuclei as a quantum object. But why quantum? Because you cannot treat it as a statistical object, because for statistical object it is a very large number of particle is needed, but we do not have that kind of particle in nucleus, because nucleus is maximum of what, like if you are even talking about 208 lead has z of 82, so maximum 208 particle we can study. So the problem of nuclear physics is that we cannot even do statistical physics, but even you cannot apply quantum mechanics fully, because quantum mechanics as we have developed it till now is more like a two body problem or a three body problem. So how do you define a nucleus as a three body problem where the entire thing is consisting of 82 or 208 particles, or more than of the order of 300 particles? That is why there is a concept of nuclear shape. What is a nuclear shape? We think, we try to understand nuclei as a collective thing, and everything that there is in nuclei is consisting of a shape or a core. So when, suppose I am talking about 100 ruthenium. Okay, so ruthenium has is an isotope where 44 neutron, proton and 56 neutron are there. So as many students must know that the ground state transition of a even nucleus is 0 plus, because all the particles are coupled. So when, if I consider it as a closed core, that even core, and then we couple of odd particle there, so there is a core and there is a particle, so that reduces the whole thing as a two body problem. But the main problem is the core that we are considering, we are assuming it as a one body, but it is not exactly a one body. So there comes the problem of nuclear physics, because we don't understand the nuclear force well. That is one of the problem. The strong force, we do not have complete understanding of it. And second, there is the assumption that the nuclear shapes are consisting of many particles, but we are assuming it is a one particle. So I hope every student understands it. So that is why when we reduce it to two body, then we can consist about think about a quantum rotation. But the problem is that it is a like the operator. This dr is the operator, and alpha r is the wave function after the rotation, and then n is the rotational axis, j is the angular momentum. But can any student from the audience answer me that why quantum rotation is not possible in a spherical shape? Anybody can have a guess, and it is not an exam, so nobody is going to cut your marks. So anybody who is willing can tell me why or guess why. If not, then I can answer. I'll wait for a little bit. No one? Okay. So when we are talking about quantum rotation is visible in the form of change of wave function. Okay. So when I'm considering a spherical shape, suppose that there is a ball and the ball is symmetric from all the axes. So even if we rotate the ball, if an observer who is not seeing the rotation cannot identify if the ball is rotated or not from the outside frame. So that is why in spherical shape, quantum rotation is not possible. Then how a nucleus is rotated? Suppose that there is a deformed shape, okay, like this, and there is a symmetry axis. But if we rotate this and it goes there, so you can understand that there is a rotation of the whole system. So this is called a deformed nuclei. And also when there is a spherical core and there is a single particle coupled to it, that is called a spherical nucleus coupled to a single particle. Here, the level scheme, or as we can see, the decay scheme, or the gamma decays, that is called the level scheme. Those are very haphazard, as you can see here. But when there is a rotational axis and there is a rotational structure, the rotational energy changes in I into I plus 1, and the spin increases. And with that, there is a symmetric kind of structure, and this is called a band structure. So for students in deformed nuclei, we can see a band structure. But in spherical nuclei and the one particle coupled to it that doesn't have a band structure, it is very haphazard. And this is due to the effect of single particle orbital. So when I am talking about the deformation of an axis, there is also angular momentum to it. So suppose that this is the this r vector here. This is simple vector algebra. This is the r vector here. This is the rotational axis of the nuclei. Okay, and then if there is a particle coupled to it, the angular momentum of the particle is like this. This is the j, and this r and j, when you vector add to it, we get the total angular momentum of the deformed nuclei. That is called the I. So if there are two projections of I, one on x-axis and one on z-axis, okay? So in z-axis, the projection is called the sigma, omega, and in x-axis, it is called the ix. Both are an observable quantity in experimental nuclear physics, and this omega is a conserved quantity when there is a deformed nuclei and a particle is coupled to it. So you can see that there are two limits to it. One where the angular momentum is more towards the z-axis and where the angular momentum is more toward the x-axis. So when there is more toward the z-axis, then it is more coupled to the deformation because it is along the deformation. So that is what called a deformation alignment. And when the axis is more towards the r vector, that is called a rotational alignment. Okay, and there is two type of coupling limit. So what is a deformed nuclei? So everybody knows that there is a shell model, and in shell model, there is a specific type of degeneracy. And it only the degeneracy of the other 2j plus 1. Suppose that there is 3 by 2 shell and there are four nuclei that can accommodate to it. So that is called a shell model. But when we like move from shell model to Nielsen model, I'm sure the third year students at least have heard about the Nielsen model. So in Nielsen model, the deformation, so the degeneracy is lifted and only two particles is allowed per shell. Okay, and this also splits according to, suppose that there is this 2D, this D5 hub, this D5 hub, D3 hub, those are splitted. As long as the deformation increases, the splitting also increases. Okay, so when we include the deformation beta 2 does what? Beta 2 does the splitting. And this is a calculation I did during my PhD. And so suppose the red ones I'm showing is the D5 orbital. Okay. And when the deformation is increased, it is splitted in half, 3 half, 5 half. Similarly, G7, the orbital is splitting in half, 3 half, 5 half, 7 half. So in x-axis, what is this? This is deformation. So as nucleus is more and more deformed, the splitting is more and more. Okay. And interestingly, as you can see that there is this negative parity H11 of orbital, because H is, if you start from S, P, D, F, G, H, if you can see that H has a negative parity, -1 to the power L. Okay, S is 0, so H gives it 5. So -1 to the power 5 is negative, so that is why H has a negative parity. D5 of is a positive parity orbital, and when there is no deformation or the nucleus is spherical, you can see these levels are well separated in energy. But as you increase the deformation, you can see the lower omega of the H11 up comes down so much that it mixes with the positive parity orbitals D5 up. So that is the main criteria of deformation, that it mixes levels of opposite parity even. So this is a prolet shape and this is a oblate shape. So these are two type of beta 2 deformation that you can see in our nuclei. And but we can also add so beta 2 is basically y20, Legendre polynomial y20. And then after you increase it more and more, you can go to the higher orders like y30, y3m. You can increase that. So beta 3 is basically y30. And y30 means what? It mixes the parity as well. Because in beta 2, the parities were not mixing. The same level parities were splitted. But in beta 3, the different parity orbitals are also splitted. So you can see here, when the beta 3 is on, there is no specific parity to any levels. Here, the parity was present or conserved. But after the beta 3 deformation, the parity is not even conserved. And this is what we called an octopole shape. So my PhD was more focused on this octopole shape kind of nuclei. So how do we populate this nuclei? There is a target, stable target. Stable means what? That it does not decay to other particles. And there is a projectile. The target and projectile is fused and a compound nucleus is formed of the order. This is the timeline of the order. And then these particles are emitted, like alpha, gamma, proton. These particles are emitted to stabilize the nuclei. After the particles are emitted, there are residual number of amount of energy left in the nuclei, and then the nuclei reaches to ground state. So that is why the energy of the particle is energy of the projectile is very important to know that exactly what we try to observe. And it is a data acquisition array that we use, and these are called clover detectors in the left. And this is a Pixie 16 digitizer system. And these photos are taken in variable energy cyclotron center. And okay, so how do a clover detector work? So as the students know very well, that the interaction of gamma with matter happens in three ways: photoelectric effect, quantum scattering, and pion production. So in the energy region of the KeV order we work in, the photoelectric and quantum are the most dominating effect. And clover detector uses those two kind of effect and give us a spectrum like this. This is a typical spectrum that we got from a clover. And this is a clover detector, and the crystals inside it are like kept in a way that it resembles a clover leaf. That is why the name comes clover detector. And the energy resolution of these detectors are very good, extremely good. And that is why we use those detectors to separate very fine lines in energy, almost 2 kV at 1408 kV. That is the energy spread of the 1408 kV is of the order of 2 kV. So what I usually do as a gamma ray spectroscopist, we do the efficiency calculation, like how efficiently an array can catch the detectors. Catch the emitted gammas, because the gammas are always emitted isotropically, right? But we have a limited number of arrays, so we cover a limited number of solid, what do call it, solid angle. Sorry, the solid angle, and so we need to understand what is the efficiency of this calculation. That is the first. And then building label scheme like this. This is a real life thing. This the snapshot is from one of my research papers. And here we solve the jigsaw puzzle. Like if there is gamma which is coming in this gate, that means that this cannot be this gamma because these two lines are parallel. So there are some logics to it, and this using this logic we put the gammas in order, and then try to understand how strong this gamma is. And also, for when you're talking about gamma, we also have to know the spin and parity of the gammas. So for that, we use DCO method, which is called a directional correlation from oriented space method, to know the spin. This does not give us the parity. It just gives us an angular momentum change of what is the gamma. And then there is polarization, the PDCO method, so that we know the parity of the gamma. If it is of electric type, it is of magnetic type, that. And also we can measure the lifetimes of levels. There are several ways to measure a lifetime, but I used in my PhD doctor sleep attenuation method or DSM method, where the shapes, as you can see, in the forward angle, the shapes are more bent like this. In 90-degree, it is a perfectly Gaussian shape. But in 40-degree or in 125-degree, in 40-degree, there is a deformation in forward, and in 125-degree, there is a deformation in backward. So that is how we estimate the lifetime. And okay, and I like try to give you a visual representation of me doing an experiment, and these are all my colleagues that I worked with. And I've been acting bomber of VCC and TIFR INGA. And my experience also includes testing of various detector, data acquisition, and data calibration, like gain matching, because if we do not calibrate things properly, the alignment will not be there, because this is before calibration, this is after calibration. So we have to, everything has to be in the proper energy lines to us to understand what is the exact energy of the gamma. So thank you. I think I finished almost on time, and if there are any questions from the audience, I'll be happy to answer.
Thank you. If you have any question, you can ask.
Okay, that means nobody understood anything. If there are no questions.
Okay, Apnalita, we have no questions. So thank you very much.
Okay, thank you.
Wait, to change করছে এটা বাইরে আমি করতে পারবো তুমি বলে দিচ্ছি
আচ্ছা আমার না
আছে দেখলাম প্রশ্নটা রাউন্ডটা মাথায় বুঝতে পারে বুঝতে পারছি নিজে ডরে দিতে আমি বলি বলি দিতে তো আটিটা ফেলে লাগি
Okay. So our next speaker is Dr. Mananya Mukherjee. So she is joining us live from the United States and will be delivering her talk online today. See again, when they join virtually, so it is always a pleasure to welcome back our former students and hear about their international research experience. She completed her PhD from our English department in 2014. After completing her bachelor's degree, Dr. Mukherjee pursued her MSc at St. Xavier's College, Kolkata, and then completed her PhD in theoretical cosmology from the University of Massachusetts, Lowell, USA. Her research focuses on understanding the large-scale structure of the universe and examining extensions and modifications of Einstein's theory of general relativity. Dr. Mukherjee works on some of the most fundamental questions of cosmology, from the rapid expansion that took place moments after the Big Bang to the mysterious force known as dark energy, which is accelerating the expansion of the universe today. She also studies how the tiny bits of matter in the early universe eventually grew into the galaxies and clusters of that we observe now. So today, Dr. Ananya Mukherjee will take us an exploration of the large-scale structure of the universe, uncovering clues about cosmic inflation, dark energy, and evolution of galaxies across cosmic time. So we are delighted to have her join us online, and we look forward to hearing her insights. So with that, I invite Dr. Ananya Mukherjee to begin her presentation. So please join me in welcoming her.
শোনা যাচ্ছে না তো? শোনা যাচ্ছে না?
Hello. Hi, Professor. Can you hear me? Okay.
Yes, audible. Yes.
Okay. Okay. Thank you. Thank you very much for the introduction. All right. So I'm going to start sharing my screen. Um, okay. Can you see my screen? Oh, sorry. Okay. Okay. I think there might be some problem. Let me just try to fix it. Okay. Hi. Sorry about that. I had to fix the share screen option. So thank you very much for the introduction. And since you all know me, so I will, and I also spent some time figuring out this. So I'll just jump straight ahead to the presentation. So today I'm going to talk about the large scale structure of the universe and what it can tell us about the inflation and the dark energy. So first, I will introduce you to the concept of large-scale structure and walk you through the origin and the evolution and observation and the theory with some mathematical equation of the large-scale structure. And then I'll talk about how the distribution of luminous matter relates with the invisible dark matter distribution. So next thing I will talk about is a very interesting topic, that's forecasting the survey performances. And then I will talk about my research and what I have found. So let me start with this picture. So this is a deep field image captured by a satellite called Euclid. So, and some more. So these images are called the deep field images, and they are high resolution 2D projection of the cosmos. But when we see the universe in 3D, so we see, when you see the universe in 3D, we see the reality. So we see that the universe is actually mostly empty space with galaxies are organized as cosmic wave. Sorry, my slide transition is little off. So to understand the full story of the universe, we need to take a step back from the individual galaxies and look at the universe as a whole. So the picture that I showed in the last slide, so what did you see? So you might think that the matter is scattered across the universe randomly, but when we map the universe, we see kind of exact opposite. The distribution of the matter is not random at all. It is organized into highly complex structure, interconnected architecture called cosmic wave. So as you can see here, the topology has three distinct components: the filaments, which were the strands of gas, which are the strands of gas and dark matter, where most of the galaxies reside, including our own. And then we have the nodes, so which are massive clusters. And then we have the voids, which are vast spherical regions which are devoid of any galaxies. And together, this brings us to the formal definition of large scale structure. When we use this term, we aren't talking just about single galaxy cluster. We are talking about these correlated patterns that extend across billions of light years that was sculpted by gravity over 13.8 billion years. To give you some idea of the scale, so the large scale structure, the spatial uh, uh, extent of large scale structure is from 10 megaparsecs to almost to 100 megaparsecs, and 1 megaparsec is roughly 3 times 10 to the power 6, so 3 million light years. Okay, so what how did it come about? To understand the massive structure we see today, we have to go back to the beginning, the theoretical origin, the Big Bang. Now, this is very crucial to remember. As the name suggests, Big Bang is not really an explosion in space, but it is a rapid expansion of the space from the initial singularity. But this leads to a fundamental problem. So since the Big Bang is a perfect expansion, so the space would be perfectly uniform. So how did these structures come about? The answer lies in quantum mechanics. So in the earliest moments of the universe, the vacuum energy wasn't smooth. So there was some bubbling. So the vacuum energy was bubbling with quantum vacuum fluctuations. So and then cosmic inflation happened. And in a fraction of second, the universe expanded exponentially. This expansion took these quantum fluctuations and stretched them out to macroscopic level. And these imperfections in the density field, they become the blueprint of the cosmos. Once the inflation ended, gravity took control, and they started to collapse under gravity. So the physics is simple. The slightly overdense regions, they have stronger gravitational attraction to their surrounding, and they attracted more matter. As they gained mass, the gravity got stronger, and they started pulling in even more matter. So over the next 13.8 billion years, this process turned those tiny quantum ripples into massive clusters and filaments that we see today. Okay. So I'll show. So you might have seen these pictures many times. So this is an incredible picture um, uh, made by the WMAP science team. So this basically shows the history, the entire history of the universe, starting from the Big Bang, and this expansion of space that we see. So this is called the inflation. Okay, so now since I mentioned about inflation, so what is basically the inflation? So after right after Big Bang, in a tiniest fraction of second after it started, so 10 to the power minus 36 second, the space started to expand faster than the speed of light, and it started to stretch so basically the universe, which was at that time at size of a subatomic particle, so it became macroscopic. And the energy density of the field driving this inflation was not perfectly smooth, and it had those microscopic quantum fluctuations, and these fluctuations, inflation stretched this microscopic fluctuations to outside of the observable universe, and it basically frees them in the fabric of spacetime, and these became the seeds of the LSS that we see today. So now the theory of the inflation. The simplest model of inflation is called single field slow roll. So in this model, what we assume is a single scalar field, which is called the inflation field. It slowly rolls down a potential hill, V phi, such that the potential energy always dominates the kinetic energy. And this drives the exponential expansion of the space. So now the single field slow roll inflation, it predicts that the primordial fluctuations that they generate, they are Gaussian, they are distributed as Gaussian. So basically the density field follows this kind of bell curve. And you might be familiar with the Gaussian distribution, like the distribution of velocity for in ideal gas samples. Now, the single field slow roll, which is the simplest theory that predicts the Gaussian distribution. Now, there are other alternative theories, and they predict complex interaction between the fluctuations, between the inflaton field itself. There are other theories, there are multiple fields. So all of these interactions, they create primordial non-Gaussianity. So that means the the fluctuations that they generate are not exactly Gaussian. So what happens after Big Bang? So after Big Bang ends, the potential energy of the inflaton field decays to standard model particle, and it creates a hot, dense, opaque primordial plasma. So plasma containing the free electrons, free protons, and photons. So for next 3.8 um, 300 380,000 years, the universe was just an opaque fog. So the photons were constantly scattering from charged particles by Thomson scattering, and the matter and the radiations were coupled together. And but universe is keep but the universe is keep expanding. So as the universe cooled to around like 3000 Kelvin, the proton and the electrons, they bonded together to form the neutral hydrogen. So as soon as the neutral hydrogen was formed, the photons were decoupled from matter. So now the mean free path of the photons were increased, and light was finally being able to escape from this primordial plasma. And this is what and at that point we see the cosmic microwave background, this magnificent picture. So, and the discovery of this cosmic microwave background is a story of itself. And if you are interested, so please explore that. Okay, so now now after inflation, after we have the primordial seeds for matter. Now what happens? Now how does the LSS evolve? So we already have dark matter. So as I was saying, the ordinary matter, the ordinary matter was coupled to electron, but the dark matter was not coupled to electron. So it could just collapse and it could form deep gravitational potential wells. So these potential wells, they acted as a scaffolding for the baryonic matter to later. So when the baryonic matter was decoupled from radiation, so it could collapse to these scaffoldings. So and after it started collapsing post recombination, and gravity again started to do the gravitational collapse process, and it started evolving um, from the small structures to the cosmic wave we see today. So this is a movie of this is a video of the simulation of dark matter particles. So how they so starting from almost an uniform distribution, how they collapse and form the large scale structure. So the next slide. So this is just a still from the simulation. So as you can see, starting from the almost initial uniform distribution with some primordial seeds, so it started collapsing under gravity, and finally we have some large-scale structure. Okay. So before we dive into the topic of large-scale structure, I want to just take a detour, and I want to spend like next few minutes to go through the overview of cosmology. So everything we do in cosmology, it started with a discovery that changed the reality of in 1929 by Edwin Hubble. So before Hubble, so there was a consensus that the universe is static. But Hubble's observation of distant galaxies showed that the galaxies are they are basically rushing away from us. So he established that the universe is not static, but it is dynamic and it is expanding. So how do we measure this? How do we measure how fast the universe is expanding? So we use redshift. So as photons travel through the expanding universe, space stretches it, right? So this stretches the wavelength of the light by comparing the wavelength that we receive in our telescope to the wavelength emitted by the atom. We get the redshift. So that's this equation Z here. So this is not a traditional Doppler shift because the space itself is changing, because the space itself is expanding. So it's called the cosmological redshift. This brings to the other important parameter, which is called the scale factor, and scale factor is related with the redshift. So today the scale factor is 1. And in the past, the scale factor was less than 1. Okay, so and Hubble's observation, and from the observation by Hubble, so he also formulated the celebrated law of Hubble's law, that the velocity of the recessional velocity of galaxies is proportional to their distance, and the proportionality constant is the Hubble constant. And this is and also, so the Hubble parameter that we have, it's defined this way as the derivative of the scale factor with respect to time, and the Hubble constant, which is different from Hubble parameter, so which is the present day value of the Hubble parameter. So right now it's measured as 100H. So H is a parameter that we use because there are some discrepancy regarding measuring the Hubble constant. So now let's look at the mathematical framework of cosmology. So we use the general relativity by Einstein. So so the equation of motion that we use for in cosmology, it starts from Einstein's field equation. So the left hand side of the equation, we have two terms. So we have the g mu nu, so which tells us the geometry of the space time. So lambda is the cosmological constant, which I will talk about later. And this little g mu nu, so this is the space time metric. So metric is basically like a ruler for the space time. And on the right hand side, we have this term T mu nu. So T mu nu, it's the distribution of matter and energy. So John Wheeler famously said that to interpret this equation, you can think of matter tells space how to curve and space tells matter how to move. So the full Einstein's field equation is a very complicated 10 coupled partial differential equation. To solve this is a very hard job. So basically what we do, we cheat and we use the cosmological principle, and we assume that at sufficiently large scale, beyond 100 megaparsec, the space is uniform and isotropic. So when we impose this symmetry, the metric, the space-time metric, the little g mu nu over here, so it reduces to the flat FLRW matrix. So FLRW stands for Friedman, Lemaitre, Robertson, and Walker metric. And so when we plug this metric into the Einstein's field equation and we solve for the 0/0th component, we get the Friedman equation. So Friedman equation, so basically on this side you have, on left hand side you have the Hubble parameter. On the right hand side we have energy density and the space-time curvature. So the energy content, so what's the energy density? So we assume that the universe is made up of different kinds of fluids. So there are matter, radiation, dark matter. So the energy content is typically given as omega. So which is a ratio of the energy density of that species over critical energy density. Okay. So up to this point is fine. Now, around 1998, so we have another problem. So since the gravity is attractive and the universe is full of matter, so it was generally assumed that the universe, the galaxies are going to pull each other, and it's the expansion of the universe is going to slow down over time. But in 1998, two teams of scientists, they were measuring the brightness of distant type 1a supernova. So they were basically trying to measure how fast the universe is slowing down. But what they found was exact opposite. So they basically found that the fainter um, um, they found that the universe is basically um, expand the expansion that is happening. So it's basically accelerating. Um, so so yes, so we have this equation. So we have the acceleration equation, and if the acceleration is increasing, so that means this right hand side of the equation is positive. So that basically boils down to negative pressure. So this started the idea of dark energy. So some unknown species of matter with negative pressure. And for this incredible discovery in 2011, these group of scientists, they were awarded the Nobel Prize in Physics. So this is the second time people got Nobel Prize in Physics for in cosmology after the discovery of CMB. Okay. So now the lambda CDM model. So the lambda CDM model is the most popular, most widely accepted model of cosmology. So when we pull all these observations together, the expansion history from supernovae, the initial conditions from the cosmic microwave background, and the matter distribution from the large scale structure, we arrive at the coherent picture. So we call this model as lambda CDM, or the concordance model. So you can think of this as a standard model in cosmology. And it is and it can be parameterized. The model can be parameterized with some simple parameters like Hubble parameter, matter content, cold dark matter density, and then we also have other parameters which are related to inflation. So in this model, so we assume that the dark energy, so there are dark energy almost 70%, dark matter 26%, and the rest of it is visible matter, the baryonic matter. Okay, so how do we actually gather these data? So we rely on cosmological surveys. Unlike traditional astronomy, we often focus, in astronomy, we often focus on specific individual objects like some star or some black hole. So these surveys are industrial scale experiments. So they are either ground based or they are either space based. So their goal is basically to map the statistical distribution of matter across the entire visible volume of the cosmos. And we generally categorize these cosmological probes into two families. So one looking at the CMB radiation, and the other one looking at the large scale structure distribution. So now CMB, so CMB probes are very old. So they are so they have been starting to do CMB experiments from early 1990s. So started from WMAP. So CMB is a 2D snapshot. It's basically a 2D snapshot of the universe. And it is already, the constraints are measured extremely precisely. But on the other hand, the large scale structure probes, so they provide the 3D map of the universe. And so since it's a 3D map, so we have more data, we have access to more modes, and so potentially in the future, the large scale structure surveys are very, very promising. And that's what I want to focus on. Okay. So the galaxy observables. Now, the crucial point. So when we look at the large scale structure, the map, the 3D map, so we see the specific galaxies, millions of galaxies at specific location. But whatever theory we have, so those theories do not exactly predict the location of individual galaxies. So the theory doesn't say that, oh, this galaxy will be at position XYZ. But what they do is they predict the statistics of the field. So that's why we cannot just we need to see their statistical distribution. So for that we use 2-point correlation function, 3-point correlation function, or higher correlation functions. So what these 2-point correlation function is, so it's basically the product of the average of the product of two density field in Fourier space, and the 3-point correlation function is product of three density fields in Fourier space. So that's called the bispectrum. And these are typically the observables for galaxy surface. Okay, so now time for some math. So the theory of LSS. So this slide, I'll just show you the equations that we use, but not too much in detail. So first, as we like to do, so we assume a distribution of matter particles at position r, velocity v. So we can write their equation of motion in terms of the velocity and the position. And finally, we can also, if we have their distribution of mass, then we can write a Newtonian gravitational potential. So so this picture, so on the right hand side, so you can see it. So this is a snapshot from the dark matter simulation that I was showing earlier. So here the matter field is not uniform, so it is clumped at spaces and at several places. So the density contrast we can write as at some point x and tau as rho bar, so which is the average density, times 1 plus delta. So delta is called the overdensity, and we are interested in studying the overdensity. And also the total velocity of these matter particles is the Hubble flow, as I was mentioning that. So plus there is another component of velocity which is called the peculiar velocity. So the Newtonian potential. So now we have two types of velocity. So there are two types of potential. So the Newtonian potential we can write as the first term on the right hand side is coming from the Hubble flow part, and then the other term is coming from the gravitational potential, the peculiar velocity. And we can also write a Poisson equation, so where the gravitational potential is sourced by those overdensity. So then from Poisson's equation, if we do some mathematical steps, so we can write down an equation for delta and the peculiar velocity field. So and remember, this is in linear regime because these equations are extremely complicated. So when we see the full nonlinear regime, but this is a very simplified version in linear regime. So now we want to study how the delta, the overdensity, is evolving. So we basically split the overdensity in two parts. The d, which depends on time, so which evolves with time, and then delta x comma 0, so which is the initial overdensity that doesn't evolve with time. And so in the last slide, I showed you two equations, and if we do some manipulation, we can get a second order differential equation for the growth factor d. And then another quantity that is very interesting to us is growth rate, so which is the logarithmic derivative of the growth factor. So why f is very important to us? Because so if we assume that the GR is correct, then we get an equation, we get some predictions about the growth rate. But if we assume GR is not correct, then the growth rate will be very different from what it used to be in GR. And I want to highlight here one of my earlier work where I looked at the theory of massive gravity. And in massive gravity, so we basically assumed that the gravitons, the particle which mediates gravity, so that is massive, and the massive gravitons. So if in that theory, in the theory of massive gravity, if we calculate the growth rate, that is significantly different than the lambda CDM. And if we observe something like this, that potentially signals departure from GR. Okay, so now I want to talk about how the luminous matter, which are the galaxies and clusters of galaxies, they are related to the underlying dark matter. So this is a picture. Inside, you can see the Hubble deep field images, and outside, this purplish region is from a simulation, and it's showing the distribution of the dark matter. I introduced the dark matter over density delta. The same way, you can also write a galaxy over density, so which is delta G. And delta G is, so we can write delta G is some parameter times delta, which is the galaxy over density is something times dark matter over density. And this parameter B, which is called the bias parameter, is not equal to 1. So what does that tell us? That it tells us that the distribution of luminous matter does not exactly follow the underlying dark matter distribution. So this relation is very important. This is called galaxy bias, and I work on galaxy bias. So this equation is, the first equation is very simple, delta G equal to B times delta. But in general, the galaxy bias equation is pretty complicated. So we have so the delta here. So the last equation is the general equation. So here we have the operator O. So it is made up of delta and the power series of delta and its spatial derivative, which are and also the tidal fields, and then we also have the statistical fluctuations. Okay, so my current work. So what I'm currently doing. So we started with this theoretical curiosity that how well future galaxy surveys, especially Euclid, the picture which captured the first picture, is going to measure the cosmological parameters. So whether it can tell us more about the mechanism of inflation, or if there are any modifications to GR at large scale. To explore the inflationary mechanism, we started with this assumption that the primordial fluctuations which were generated during inflation are non-Gaussian. Since we know that the simplest and the most popular theory tells us otherwise. So if we can detect non-Gaussianity, then for sure we can say that the inflationary mechanism is more complex beyond just single inflaton field. The inflationary potential. So first we write the inflationary potential as non-Gaussian. So so we start from the Gaussian potential and we do a Taylor expansion and we write the final non-Gaussian potential. And we parameterize this with a parameter called FNL. So FNL basically tells us the degree of non-Gaussianity. So and the next step, the first step of the problem is this inflationary potential phi, how do we relate it to dark matter over density? So after doing some tricks, we can finally write that how phi is related to delta. So it relates through transfer function, and the transfer function basically encodes the evolution through different epochs. And then so when we observe the universe through these large-scale structure surveys, we are not seeing all the galaxies out there. So we are seeing a specific subset. This selection is based on several properties, like how the galaxies are oriented, what's the brightness of the galaxy. If it's too dim, then we cannot see it. Since the galaxies are observed along a line of sight, so we introduce some terms. So in the galaxy bias relation, we introduce some terms which are dependent on the line of sight, and we call these as selection effects. And the bias parameter is beta. And also, since from cosmological surveys, galaxies are not measured from their redshift space position. So they are measured from their redshift space position, not the rest frame position. So we do the transformation, the coordinate transformation to change the galaxy delta G in rest frame to delta G in redshift space. So while we do that, so we also see a bunch of terms which are called redshift space distortion. And with all of these, incorporating all of these effects, we want to check how tightly the Euclid survey can measure the lambda CDM parameters. Okay. So the survey forecast. So since the cosmological surveys are high stake, high risk, high budget projects, so it is absolutely important to make some predictions before we actually start observing them in space. So this is the domain of forecast studies. So here, first we compute the galaxy observables, like the endpoint functions, the power spectrum and bispectrum. So which depends on the model parameter. Then we construct Fisher matrix. So one of the key advantage of this technique is that, so first we just assume a fiducial value for fiducial or the value which are already accepted for these parameters. And then we can compute the 1 sigma errors without requiring any observational data. So this is before the survey even launches. So this is a very powerful tool. So as it allows us to forecast the expected error before beginning the survey. So suppose we have a set of data point x, and then it depends on model parameter theta. So the Fisher matrix, the diagonal element of the Fisher matrix gives us the variance of the parameters. So which are so from the variance we can compute the 1 sigma uncertainty. And the off diagonal elements are also very interesting. So they indicate the correlation between them. So correlation is basically like how correlated two parameters are. If I measure one parameter theta 1, so how much so is it going to affect the measurement of theta 2, something like that. Okay, so we can compute the Fisher matrix, and we get the 1 sigma error. So how do we visualize it? So we visualize them through the confidence ellipses. So basically the shape and the tilt of these confidence ellipses tells us what's the 1 sigma error, what's the fiducial value. So the larger the ellipse, it means low precision. The 1 sigma error is more. 1 sigma error is more. So and the data is less sensitive. So leaving us with larger uncertainties. And the tilt. So if there were any tilt along one of the axes, then we can say that these parameters are correlated. Okay. So finally, I'm going to show you the results that I have. So these are the results of our 1 sigma errors of various lambda CDM parameters. So on both axes, you can see the parameters like Hubble parameter, the cold dark matter contents, also the growth rate F, which is very interesting for us. And these ellipses, so what these ellipses tells us that the lighter blue region is when we just take power spectrum as the observable, and the darker blue region is the when we take both power spectrum and bispectrum as observable. Okay, and so this is the result when we ignore those line of sight dependent selection effects. And this is our final plot. So where we have included those line of sight dependent selection effects. So as you can see, the 1 sigma error has increased. So when we add those line of sight dependent effects, the constraining power was weakened for the, so basically the lighter blue regions have grown bigger. So that means the constraining power has weakened. But as we add the bispectrum, so which are these darker blue regions, so they are again, they have shrunken. So that means the whatever constraining power that we lose by just adding the 2-point correlation function, if we add the 3-point correlation function, then it is mitigated. So okay, and this is this is another plot. So here I'm just showing the 1 sigma errors as bar plot. So the main point that I want to highlight is the value of FNL, the PNG parameter. So this value was measured by Planck satellite. So Planck is a CMB survey. And if you see the 1 sigma error, which is 5.1, and if you look at our best estimate of the 1 sigma error, so which is close to 2, maybe this is pointing to the fact that future LSS surveys are going to be more powerful in constraining the parameters. Okay, so here is my summary of whatever I have found. So definitely the LSS are very promising probes to measure the parameters. So upcoming LSS surveys are going to probe such vast volume of the universe. So then it will be very important to add those line of sight dependent selection effects. And when we, from our analysis, we have found that when we include those kind of effects to reduce the measurement uncertainty increases. And to reduce the measurement uncertainty, we definitely need to include the bispectrum, the 2-point correlation function. And we have also seen sufficient degeneracy between because yeah, so I want to point out to this ellipse. It's very tilted between beta and F. So there is a very high degeneracy. So when we only do power spectrum only analysis, but when we add the next higher order statistics, then the degeneracy has those ellipses has shrunken. So basically, the constraining power has increased. And also, the main thing is there is no degeneracy between the PNG parameter and the line of sight dependent beta parameter, and between the PNG parameter and the growth rate. So they can be measured independently. So which is very promising. And yes, I think I have gone over. And yeah, please. Yes, thank you. I'd be happy to take questions from the audience.
Thank you so much, Ananya, for that wonderful and insightful talk. Sweet. If anyone has a question,
Thank you, Ananda. I have a question. That,
Yes, please.
Your field is totally specialized apart from our knowledge. But one question came to my mind that since you told that universe is expanding, galaxies are expanding. So what is the fate, ultimate fate? Whether it will burst out or whether there is a limit, what is the fate you have calculated or any idea about that?
Yes, so that's a very interesting theoretical question. I think sorry. There seems like a feedback. Can you hear me all right? Yes. Okay. So yes, I don't know the answer. So the consensus is that it will slow down after. So right now the expansion is accelerating. So it's expanding faster than it should. So but ultimately it's going to slow down, and after that I don't know. Sorry, I cannot hear you, ma'am.
One more question came Ananda from Andorra.
Yes. Yes.
Hello, absolutely nice talk. I am on
Hi. Thank
I
you.
think
Yeah, hi.
possibility. So a little question. Like
Yes.
you spoke that consider the bispectrum and power spectrum and the constantly constraints more actually depending that. So if you
Yes.
consider the price spectrum, then also it will get better for but
Yes, absolutely. I agree. But the problem is they become computationally more expensive. So it takes more computation power. So the goal is to use the like the lowest order correlation function that we absolutely need to use. And my work was basically figuring out that if we add those line of sight dependent effects, then what happens and what do we do to like mitigate it at the minimum cost.
Any other question? Okay, so we do not have any other question. Thank you, Amanda.
Thank you very much. It was an absolute honor
কিছু
to
বলতে চাই
be
যদি
one of
ভুলে
the
বাড়ি যাবো
speakers. Thank you.
বলো
And thank you to professors for giving me the opportunity to present here, and it was an absolute honor. And I would be really excited to be there in person, but yeah, thank you.
God bless you. God bless you.
Thank you very much. Thank you. Okay, so I'll drop off from the call, and I think the next presentation will be in person since Antara is there. So
On করা।
Our next speaker is Dr. Antara De. She is present here. So she completed her BSc from Physics department in 2015. So it is always a proud moment for us to welcome back our former students who are now doing exciting research in leading institutions in our country. So after completing her BSc, Dr. Dev pursued her MSc at Rajamaja Science College and went on to earn a PhD from the Indian Statistical Institute, ISI, Kolkata. So incidentally, our colleague Dr. Dikti Banerjee also did a PhD from there. And so they are likely to feel an extra connection. Of course, also there. So Dr. Antara De is currently a postdoctoral researcher at the Institute of Physics, Bhubaneswar. So working in the field of cosmology. Her work focuses on the early and late universe, including dark matter phenomenology and 21 centimeter wavelength radiation cosmology. So she is also part of the Square Kilometer Array project, which is one of the world's largest upcoming radio telescope. So today, Dr. Dev will take us through a fascinating journey across the cosmic history. Her talk will help us understand how the earliest structure formed and how the universe evolved into what we observe today. So we are delighted to have her with us and we look forward to hearing her insights. So now I would like to invite Dr. Antara Dev to deliver her talk. So please welcome her.
ওই সমুদ্র মিলাতে একটা ইয়ে করা হয়েছে ওই টিকিটিটা পাঠানো হয়েছে
introduction.
ঠিক আছে আর একটু নাও অন্তর একটু নামিয়ে নাও তো এটা এইটা ল্যাপটপটা অতটা না আর একটু তোলো হ্যাঁ ঠিক আছে
I would like to express my sincere gratitude and thanks to all the professors who taught us. Because of their blood, we are today. And today I would like to discuss a very brief introduction of what I do in my PhD, like from the first life to today, journey through the universe and multi-aggregation. So as already also told that the same picture, the timeline of the universe. The universe started with the very early, like at the Big Bang. Because of the Big Bang, the universe started, and after that there is a phase called the inflation. Like at the very small amount of time, the universe expanded exponentially. So this is the period of inflation. And the fast light of the universe in the form of the cosmic microwave background radiation, we found that where the photons actually decouple from the rest of the matter. And after that, there is a phase that is called the dark ages, where there is no signal like stars, no galaxies. And after that, there is a fast structure formation of the universe started, like the neutral hydrogen, neutral helium. And after that, the stars and the galaxy. And what we announced today is here, like it is the era of the dark energy, that is the expansion of the universe. So this is the same picture, the formation, the fast formation of the structure. So after the CMB, like when the fast photons decouple from the rest of the matter, so these photons travel freely in the intergalactic medium. And as you can see, at that point of time, the fast atom, like the neutral hydrogen and helium, started to form. And these photons basically ionize the neutral hydrogen and the helium in the universe. So these small bubbles are the ionized bubbles. So in my later slides, I will also explain what we do today. And as the time progresses, this ionization basically overlaps between each other. And today, the whole universe is ionized. And the only small patches of the neutral hydrogen or helium we can see in the dense core of the galaxies. So this is the fast sky of the universe, like as I already mentioned, the cosmic microwave background radiation. So the cosmic microwave background radiation is a uniform, and the isotropic radiation, which is all uniform around the whole sky. But what we see today is that in the picture, there is a small, teeny, tiny patches. So these are the temperature fluctuation. So the temperature fluctuation, the order of it is of the order of 10 to the power -6. So as you can see, the whole universe, the whole sky is uniform, but the fluctuation is of the order of 10 to the power -6. Very small fluctuation. This small fluctuation is actually the seat of the structure formation of the universe, what we see today. So as Anandali also discussed that what is the discovery of cosmic microwave background radiation is also a very exciting. Like in the 1963, the Anjo Penzias and the Robert Wilson, they are two astronomers. They discovered like they are working in their lab on the Milky Way galaxies, and they are collecting the signals. And at that time, they found some mysterious noise in the signal. And first, they found that it may cause of the pigeons in the, and like they are found that there some noise. But after that, they confirmed that it is actually a signal which is coming from the very far away from the universe. So that is how the discovery of cosmic microwave background radiation has occurred. And it is the spectrum, the energy spectrum of the cosmic microwave background radiation. It is actually the black body follows a uniform temperature distribution like a black body curve. And it is actually the first detection of the CMB microwave background radiation, which tells us that it is exactly follows black body radiation. And because of this discovery, it is the John Muller and the F. Booth, they got the Nobel Prize in 2006 for the discovery of the black body spectrum of the cosmic microwave background radiation. So after the cosmic microwave background radiation, the first formation, the first atom like helium and the hydrogen started to form in the universe. And after that, they collapsed and dark matter is also there. I will explain that thing. And that is how the first star of the universe has started to begin. And inside the after the first structure formation has started, the dark matter is also there. There is formation of galaxies and the star. And inside the HD galaxies and the star, there is the neutral hydrogen. So actually, the cosmology is a subject which is basically driven from the observations. So here, so it is the discovery of the dark matter. So as we also know from the Newtonian physics, like when the two objects is gravitating among each other, so what will be the velocity of that particular galaxy? So if you plot the V versus the R, the radius, velocity versus the distance of this galaxy, so from the Newtonian physics, you can think of it is actually proportional to 1 by root square of R. So if you go far beyond the radius, then the velocity will fall. So this is expected from the theory, like what we know from the Newtonian gravity, Newtonian physics. But actually, when the people observed in the coma cluster, they found that actually the curve is actually not the same with the theory. It is something else. Like there is a huge deviation between those two curves. So in order to fit, like what kind of new thing is here because of this, this actually is the data. So you can also see this is the error bars, like this is the actual data plot. So people have confirmed that it is because of some special kind of matter present in the universe. Because of this, there is a curve is deviating from the theoretical point. So this is the main signature of the dark matter. Why it is called dark? Because this particular matter has only the gravitational force. They can have interact with other particles with only gravity, not any other forces. So this is the first experimental evidence of the dark matter. So our galaxy is only one among the millions of the galaxy. So you can see we are doing research in cosmology, and there are millions of galaxies. It's the only one. Cosmology, what's the distance between the two galaxies? So in cosmology, we call the distance in terms of megaparsec. So 1 parsec is type of 3.26 light years apart. So as we can see that the distance between our galaxy, Milky Way, and the nearest galaxy, Andromeda, the distance between the two galaxies is almost 3.5 billion light years. So in cosmology, what we call a distance, like the measure scale is like a 1 megaparsec, like 10 to the power 6 parsec. And it's a huge distance. And another groundbreaking observations of the cosmology is the come from the Hubble telescope. As Anunadi is also telling, like people have observed that in the Hubble telescope, like if you observe the Hubble telescope has observed that the two galaxies, they are receding among each other. So this is the recessional velocities among the galaxies, and this is the distance. So as we know from our school days, the objects who are acting among each other and which have only gravitational interaction, they have some attraction force. But here, from the Hubble telescope, we can see that those objects which are connected through gravity, they have some repulsive force. That is telling that if we go far distance away, the recessional velocity will be much bigger. So here,
the thing that Hubble telescope is telling us that our universe is expanding. Like the two galaxies are moving far away from each other. So as you can see in a balloon, if we just point some dots and if we inflate the balloons, that's the why that the 2 points are moving away from each other. So this is the case that our universe is expanding. And because of this expansion, we can also see the redshift effect. Redshift effect means in the laboratory, if we see only a particular spectrum of any atom, and if that signal is coming from very, very large distance, very distant galaxy, the signal will be redshifted, like its wavelength will be increased because of the expansion of the universe. So this is the redshift effect. So far, like from the observations, so our understanding of the universe is the universe, there is matter in the universe, which does not know what type of the matter is this. It is actually under the current active area of research, that is the dark matter. And the next thing is what is the reason for the expansion of the universe. So that is the dark energy. And because of this expansion, the light from the very distant object gets redshifted. So from our understanding of the universe, if we consider this flow, the 70%, only maximum 70% of the energy budget comes from the dark energy, which we actually don't know what is this. And apart from that, the 30% is only the matter. And among that 30%, only the 20% we know, which is called the baryonic matter. So this matter and the other thing, like the left 8% is the dark matter, which we actually don't know what kind of particles are this type of dark matter. So from this 20% of the baryonic matter, so all the stars and all the newtons like us, we are also formed this kind of type of matter. So as we can see, this is the same picture, the timeline of the universe. Like here, the late time, like here, this is the present time. And it is now the expanding universe, like it is the dark energy dominated universe. So now coming back to the theoretical model, since we have already discussed what are the observations, like from the observations, we know that there is a dark matter, dark energy in the universe is expanding. So to fit that observations, so there is a theoretical model. So what we call is a standard vanilla cosmological model, Lambda-Serial model, where there are some parameters, few parameters in the standard Lambda-Serial model. Where there are baryonic density, which counts what are the number density of the baryons, the cold dark matter density, and the Hubble parameter, how the galaxies are receding from each other. And there are some other parameters which are some early universe parameter. And here we can see there are some data, like from the observations, like there are satellites, the Planck satellites are there. This result is from the Planck satellite. So Planck satellite has given us some data, and we theorists have some model like the basic standard vanilla Lambda-Serial model. So our task is to do the statistics, like how the theoretical model will fit the data. So here, these are the basic parameters, like the 6 Lambda-Serial parameters that actually fit the observation, the Planck 2018 data. And this told us, like, these are the very successful model of the cosmology. That is a standard Lambda-Serial model, which can explain all those things like the dark matter, dark energy, and this also fits the data. But there is a catch. Like the standard model of cosmology is the most successful theory of the universe, but still there to catch. That standard Lambda-Serial model cannot explain very much. Like there are some tensions in the cosmology. Tensions means like, as I have already mentioned, that cosmology is a data-driven subject. So there is, at the early universe, there are few data like Planck, but the recent time, like there are some data from the supernova, like from the many other galaxies. So this tells us like that the H0, the Hubble parameter, there are some discrepancies in the observations, like it is apart from the 5 sigma. Like some of the observations told that the incidence should be of 64 to 65, and some other told that no, it might be higher. So it is a very serious tensions in cosmology. And also there are some tensions in lambda CDM model, which is called the sigma tension. So it is basically related to the structure formation. So apart till now, so there are lambda CDM model is a very successful theory of the universe, but still there are some like problems in the lambda CDM. Like we do not know what is the cause of the Hubble tension. We do not know what is the cause of the structure formation, like sigma tension, and also we do not know what is the nature of the dark matter, what is the nature of the dark energy. So these are all the active area of research in cosmology. So coming back to my work, so I work mainly in 21 centimeter cosmology. So why 21 centimeter? I will explain in a bit. So I have already explained like fast signature of the light is coming to us in the form of cosmic microwave background radiation. So this radiation is basically when it decouples from the rest of the matter, it travels intergalactic medium and it basically ionizes the neutral hydrogen in the intergalactic medium. So as you can see, these are the small ionization patches in the universe. And as time progresses, this ionization becomes bigger and bigger, and the ionized bubbles start to overlap among each other, and till now the universe is becoming fully ionized. So only the few fractions of the neutral hydrogen can be found in the inside core of the galaxies. And here there is a very nice signature of the 21 centimeter signal, which is a hyperfine transition of the neutral hydrogen. So there is a interaction between the electron and the proton magnetic moment. Because of this, there is a transition in the hyperfine level, and it causes radiation, which is of 21 centimeter in wavelength and 1420 megahertz in the frequency. So this is a very useful tool to know what are the things, what are the dark matter in the universe, what is the nature of the dark matter. I will explain it in a bit. So as you can see in the picture, like this is the cosmic microwave background radiation. So when the photons from this cosmic microwave background radiation comes and they travels from the intergalactic medium. So in the intergalactic medium, there are lots of stars and the galaxies. So in the stars and the galaxies, there are also neutral hydrogen. So these photons interacts with the neutral hydrogen in the intergalactic medium, and this basically boost the neutral hydrogen transition. So the CMP radiation is basically a background radiation. So in the lab, when astronomers observe the radiation, they see a small uniform background radiation, cosmic microwave background radiation, and there are some small deep and some spikes. This is because of this neutral hydrogen absorption. Because those neutral hydrogen absorb the CMB radiation at some particular points, so there the dip in the radiation has seen from the astronomy. So those signatures, those deep and the emission signatures are basically given the picture of the neutral hydrogen in the universe. And since the photons are traveling from the CMB, like at the very early to till now, so they are collecting all the information of the universe, like the dark matter, dark energy. So if we can estimate, or if we can observe this 21 centimeter signal from the radio telescope, which are in the building stage, some of the radio telescope are in building stage, some of the radio telescope already we have. So from those data, we can infer that what is the nature of the dark matter, what is the signatures of the neutral hydrogen in the universe. So coming back to my work, since there are lots of problems, lots of tensions in the standard lambda CDM cosmology, so there are few people are working on different type of models, like consider the dark matter interactions with the massive neutrino. So there are few, these are the perturbation equations for the dark matter massless neutrino interaction. So basically, because of this interaction, the blue part are basically the modifications because of this type of interaction. And since we are considering the dark matter is interacting with the neutrino, so from the equation also we can see because of this interaction, the neutrinos are basically dragging the dark matter. The main, what we see today, the structures, the main responsible for structure formation is one of the main responsibility is from the dark matter. Since here the neutrinos are basically dragging the dark matter, so it basically hampers the structure formation of the universe. So these are few flaws because of this type of interaction from the Planck. We can see that from the Planck data, so we can also see some signatures of this type of interaction. And like in cosmology, what we do today is that we do some statistical analysis. So these are the clusteria distribution of the dark matter neutrino interaction model, where U is the interaction parameter. So from the Planck 2018 data, so it tells us that the interaction parameter should be of the order of 10 to the power minus 4. But you can see that there's the upper bound is of the order of 10 to the power minus 4. But the U equal to 0, that is the zero interaction between the dark matter and the neutrinos are not actually excluded. Okay, so this actually motivates us to investigate this type of interaction in further, like in late time observations like 21st century cosmology and other observations. So for this type of observations, so what we did is we did some semi-numerical simulations, and these are some few technical points like from the observation. I am just to mention, like for the dark matter neutrino interaction model. So we do some kind of semi-numerical simulation to generate this type of structure partition law. So as in the very beginning, I have shown some of the figures, like there are some ionized bubbles, so which basically photons ionize the neutral hydrogen in the medium. So these from the simulation, we can actually have those kind of pictures. So these are the basically the ionized bubble of the in the intergalactic medium. So as you can see, if there is some signatures of the dark matter neutrino interaction, so they are hampering of the structure formation. The ionization bubbles will be changed. And from the data, from the astrophysical data, so there are some data like which indicate that what will be the ionization, like what amount of the ionization should be present in the universe. So, and so from the data, we found that for a particular redshift, like at redshift 8.0, so there should be 50% ionization in the universe. So, in order to maintain this observation, in order to maintain that the 50% ionization in the universe, so what we actually do is that we increase the photon number efficiency. So in order to increase the photon number efficiency, we found that there is a constraints on the interaction parameter, that is U. So what we found from our analysis is that in order to achieve 50% ionization at a particular ratio at a particular time, there should be a limit in the dark matter neutrino interaction parameter, which is of order of 10 to the power minus 1. So earlier from the Planck 2018 data, so people have shown that the interaction parameter, the dark matter neutrino interaction parameter should be of the order of 10 to the power minus 4. But from the 21st century cosmology, from the late time observation, we can see that the interaction parameter is of the order of like 10 to the power minus 7. It cannot be higher than that. So it is the era, like the 21st century cosmology and the upcoming observations, square kilometer array, and all the observations are very much exciting, since this type of observation can actually rule out or constrain more dark matter models in a much more tighter way than what we have today. So as I have already told that some of the radio telescopes are already there, like the GMRT, Giant Meter Wave Radio Telescope, is in Pune. They have some also data about the neutral hydrogen in the universe. But I am a part of the some square kilometer array, which is the largest radio telescope, which is in the building stage, and India is also a part of the square kilometer array. So these are some technical details of the square kilometer array, and these are some noise plot for the particular telescope. And what we did is that for our dark matter neutral interaction model, we have shown some comparison of the signal to the noise power spectra. So these are the noise power spectra. So these are the signal power spectra, and these are the noise because of these instruments. So from our analysis, we can see that for a particular scale, range of scale, the signal is much higher compared to the noise. So the signal to noise ratio is of the order of 5. So there is a huge prospects in the future that when the actual square kilometer array data will come, this can actually measure, this can actually tell us is there really a signature of the dark matter neutral interaction in the universe model. So there is a possibility to detect the signature in the square kilometer array observation. So the conclusion is that the 21 centimeter observation is actually improves the constraints of the dark matter neutral interaction model by few orders of magnitude. And this is pretty good, like from the earlier observation, like the Planck and the other cosmic microwave background radiation. So this type of constraints are very much poor, like it is of the order of 10 to the power minus 4. But the late time observation, the 21 centimeter cosmological observations, or from the telescope, the square kilometer array, or any future data which will come, it will actually play a significant role in order to detect the signals. So as I am mentioning that I am a part of the square kilometer array, so this is a small, there is an exhibition of the square kilometer array, and I was there for the demonstration. And thank you very much. So if you have any questions, please.
In today's computer applications for programming is very necessary. So in your experiments and your papers, so this program helps you, or in how they help you throughout your projects?
Yes. Actually, the thing is that in order to, like I have already mentioned, these are some simulation plots. In order to do simulations, you need to know some basic packages, like many codes are in Python, in C, and now people are doing in these are I have done in terminal simulation, but now people are doing in the machine learning algorithm that they use. So you should learn those packages. And when you do research, like you have some basic knowledge of these packages right now, or you are developing those you're learning. And when you do research, so this will help you to build and to know more about these simulations. And if you have the basic knowledge, then you can also contribute. Like there are, I've shown this type of simulation, but there are also some limitations. Like there are some assumptions. So if some are the theoretical assumptions, some are the from the computational perspective. Like already the previous speaker has shown that there's these actually simulations are being done from a supercluster, like supercomputer. They are like a month or so. It is actually this time frame, 1 month or so, it is taking to generate a one plot. So you have to generate multiple plots to show that it is actual figure. So it is necessary. Yes, it is absolutely necessary to learn those packages in your BSc data studies. Theoretical, you have to know what are the theoretical knowledges you have. You have to like push your limits to know the theory and also side by side the computation. Like nowadays in cosmology, there is no pen and paper calculation. There are few pen and paper calculation, but they are actually, if they ruled out from the observation, like these are actually thrown away. So you have to know the theory also and the experimental, like those packages also. So it will be good. So
অন করেছি তো। অন করেছি তো।
Hi, Antara, can you hear me?
ওইখানে দাঁড়িয়ে
Hi, Antara, can you hear me? Okay. Thanks. Excellent talk. Excellent work. So I'm just curious about the dark matter neutrino interactions that you see. Is there any signature of these interactions in power spectra? Because I know there are some interactions of BAO in power spectra, those oscillations, but
I have actually seen. So you can see that this is the power spectrum plot. So this is for the lambda CDA. And if we increase the interaction parameter, I have done just it is the picture is shown for 10 to the power minus 2 and 10 to the power minus 3. Because neutrino is basically dragging the dark matter, so there will be a suppression in the power at the like small scale. So because of this type of interaction, there will be some oscillation. And
yes.
what from Planck, the upper bound on this is of the order of 10 to the power minus 4. So this is the people have done this type of research where they tell us that the upper bound is of the order of 10 to the power minus 4. But from our research, we found that it is actually the 21st centimeter cosmology is giving much more tighter constraints. Like if we plot this u 10 to the power minus 7, it's almost like as in the lambda city.
Okay. Okay, thanks. And also in your in the plot of your posterior distribution, I saw there are many degeneracies among the parameters, but I couldn't make out exactly what those axes are. So do you have any insight on like how we see this?
Dark matter neutrino interaction. So it is 6 plus U. 6 basic cosmological parameter plus U. So
Yeah.
these basic 6 cosmological parameter, what you see the degenerate. If we incorporate the another new parameter, the U, it is the new parameter. So if we introduce this particular parameter, you can see like from the plan, like there is a 1 sigma upper bound of the parameter, but U equal to 0 is still there. So yes, from the Planck, we cannot say that there is no dark matter neutrino interaction or like yes. So the Planck is actually giving the upper bound of the on the dark matter neutrino interaction parameter, and there are the degeneracy. It is because of the lambda CDM model. And if you incorporate them like Planck plus, it is actually the data from the Planck bow plus Lenzi. Yes, if you incorporate the other data, the late time data, maybe the degeneracy will be gone. Yes.
Okay. Interesting, very interesting, and thank you.
No, I have a question.
Yes.
You talked about ionization.
Yes, yes.
So can you please briefly discuss what is the what is the importance of ionization and what it can happen if the universe doesn't achieve 50% ionization?
Yes, actually the thing is that here, yes. So as I have already mentioned that this is the cosmic microwave background radiation when the photons are decoupled from the rest of the matter. So these photons are the high energetic photons. And after that, the first atoms of the universe, like the hydrogen, they are starting to form. And we know that the ionization energy of the hydrogen atom. So these photons, which have the energies more than the ionization of energy of the hydrogen atom, they can ionize the hydrogen atom. So these bubbles are basically showing the ionization of the ionized bubble. These are. So as this ionization increases, we can see that there are ionized bubbles are overlapping around each other, and around a particular redshift, the whole universe is ionized. And also, I have mentioned that the cosmology is a subject which is basically driven from the observation. So these are some observations. This is a pretty tiny plot. So these are the observations of this neutral hydrogen fraction, like how much neutral hydrogen should be present in the universe and what redshift. So it is stating that at around redshift 8 or 7, the universe will be 50% ionized. The XH1 will be 0.5. So whenever you develop a theory, any kind of model, dark matter neutrino model, dark matter dark energy model, or any other model, you have to make sure that this your model, your theory will pass from these observations. If it is not passes this kind of observation, then your theory will be good. So whenever you are trying or developing new models, you have to make sure that it can pass those observations. Yes. Thank you.
Okay, now we'll go for the lunch session. So that is upstairs in our physics lab. Okay. So we'll try to meet here at around 15. Okay.
mute করে দিন
হ্যালো, মধ্যাহ্ন ভোজনের পর আমরা আবার সবাই মিলিত হয়েছি। এখন আমাদের একটা স্পিকার বাকি আছে, আজমিরা। কিন্তু তার আগে আমরা অনুরোধ করছি যেহেতু মনীষাজি অনেকক্ষণ বসে আছেন, তার স্বরচিত কবিতা তিনি পাঠ করে শোনাবেন। হ্যাঁ, সবাই একটু শান্ত ভাবে, পেছনে যারা কথা বলছে দেবলিনা একটু আমাদের সঙ্গে অনুরোধ রাখছি, কোঅপারেট করো। মনীষাজি নিজে লিখেছেন, সেই কবিতা উনি পাঠ করবেন, বুঝেছো? তুমি
বসে পড়বে না দাঁড়িয়ে?
হ্যালো, আজকে এখানে প্রথমেই আমার শ্রদ্ধেয় যারা আসতে পারেনি তাদের উদ্দেশ্যে আমার প্রণাম বা শ্রদ্ধা জানাই, এবং যারা আমার সহকর্মী, আমার ছাত্রী ছিল, বর্তমানে যদিও আমি এখান থেকে চলে গেছি, বেরিয়ে গেছি, কিন্তু তবুও তারা তো আমার ছাত্রী। তাদের সবাইকে আমার অত্যন্ত ভালোবাসা এবং স্নেহ, প্রীতি জানাই। আজকে এই যজ্ঞের, মহাযজ্ঞ বলা যায়, তার শুরু বলা যায় এমব্রায়োনিক স্টেজ, কিন্তু তবু তার শুরু তো করা হয়েছে, এবং সেই শুরুর যারা প্রধান এগিয়ে এসে সেই যুদ্ধের সূচনা করেছে, তার মধ্যে আমার ছাত্রী দীপ্তি, যে পরবর্তীকালে আমার সহকর্মী, এবং শ্যামল, উদয়, আরো অনেকে, এমনকি আমি বলবো যারা দূরে ছাত্রীরা আছেন এবং তারা নানাভাবে যোগ দিয়েছেন, এবং বর্তমানে যারা এসেছে তারা তাদের কিছু সময় ব্যয় করে এখানে এসেছে, সেই জন্য আমার অনেক অনেক ভালোবাসা তাদের জন্য। আমি আপ্লুত হয়েছি এই ঘরোয়া পরিবেশে নিজেকে আসতে পেরে, নিজেকে আমি ধন্য মনে করছি। কোনো এক সময় ছিল যেখানে আমি ছিলাম এদিকে, আমার সামনে ছিল আমার ছাত্রীরা, সেখানে কিছু ফিজিক্সের তত্ত্ব আলোচনা হতো। সেদিনটাও সুন্দর ছিল, কিন্তু আমি যদি আরেকটু পিছিয়ে যাই, আমি ছিলাম ওদিকে আমার শিক্ষক শিক্ষিকা, স্কুল, কলেজ, ইউনিভার্সিটি, এমনকি রিসার্চ লেভেলেও তাদের সাহচর্য পেয়ে আমি নিজেকে অত্যন্ত ধন্য মনে করি। সেই শ্যামল, সেই সুন্দর দিনগুলো বড় আনন্দের ছিল। আজকে প্রকৃতির নিয়মে বয়স আমাদের বাড়ছে, কারোর বয়স থেমে থাকে না, এগিয়ে যান, কিন্তু যে জিনিসটা থামিয়ে রাখতে অন্তত আমরা চেষ্টা করতে পারি, সেটা হচ্ছে মনের বয়স। মনটাকে আমরা সবুজ করে রাখতে চেষ্টা করি, যাতে আমরা আমাদের সামনে যারা আছে, ছোটরা বা যারা পিছিয়ে আছে, তাদের এগিয়ে নিয়ে যেতে
আমরা সাহায্য করতে পারি। আজকে এখানে যেসব ছাত্রীরা এসেছে তাদের থেকে একটু মুঠো নিয়ে আমি আমার মনকে সতেজ করতে চেয়েছি। সবাইকে অনেক অনেক ভালোবাসা দিয়ে আজকে আমি আমার একটা কবিতা লিখেছি, যেটা দীপ্তি আমাকে অনুরোধ করেছিল। কবিতাটা একটু ছেলে মানুষই, কিন্তু আমি তো ছেলে মানুষদের জন্যই লিখেছি। আর মনটাকেও তো আমি ছেলে মানুষ করেই রাখতে চাই। সেই জন্য কবিতাটা, তবে কবিতার নামকরণ করিনি, কারণ ওই দায়িত্বটা আমি তোমাদের দিলাম। তোমরা নিজেদের মনের মতো করে নামকরণ করো। আমি কবিতাটা বলছি। অবশ্য বয়সের জন্য ভুলে যায়, মনে থাকে না বলে আমি কবিতাটা লিখে এনেছি। মনের আমার বয়স বাড়ে না, শরীরের বয়স বাড়তে থাকে। শরীর মনে যুদ্ধ করে, কে যেতে আর কে যে হারে। মনের ভিতর ছটফটানি, স্বপ্নের পাখি উঠতে থাকে। দুলছে কেন দোলনা ধরে, এ কোন খেলা? মনের ভেতরে রেখেছে মোরে অবাক করে, দুইটি স্রোতের মোহনাতে। আমি চাই মোর মনের ভাষা, ভালোবাসার পাখনা ধরে। মনের বয়স পায় না, প্রাণের ভাষা দুই নয়নে। শরীরটাকে বোকা বানিয়ে চির সবুজকে আশ্রয় করে। আমার মনের বয়স পারে না, জড়িয়ে রাখি কবিতা দিয়ে। আমার মনের বয়স বাড়ে না, কবিতাকে আধার করে। সবুজের এই সমারোহে জোয়ার লাগুক সব মনে, আনন্দ আর নবচেতনার আগুন ঝরা 10 দিকে। বয়সটাকে শক্ত করে স্বপ্ন দিয়ে বাঁধ করে, তাই তো তোদের মনগুলোকে আবেগ দিয়ে জড়াইবে। এগিয়ে চলার মন্ত্র থাকুক মনের ভেতর অন্তরে। শুভ চেতনার স্নিগ্ধ আগুন জ্বলুক যেন সবখানে। আয় না তোরা, শপথ নে না, পথ দেখা না অন্ধকে। তোর আগুনে পথের দিশা মিলুক যেন সব দিকে। সবাইকে অনেক অনেক ধন্যবাদ জানিয়ে আমি শেষ করলাম। একজন এসছে, এই কারণ নাম আমার একটা এখানে বসে আমার দেখা যায় একটা বড় এবার ওই নাকি
That we have re-energized after lunch. It is my pleasure and honor to introduce our next speaker, Ms. Ashmira Sultan, an outstanding alumna of the Department of Physics, Vidyasagar College for Women. Ashmira completed her PhD in physics from our college in 2027 with first class and subsequently obtained her MSc in physics from Rajapaja Science College in 2019. Our consistent academic excellence is further reflected in our remarkable achievements qualifying NEET, and JEST, all of which speak volumes about the dedication and depth of understanding in physics. Ajmira is currently pursuing her PhD at the Renewable Energy Cyclotron Center, Homi Bhabha National Institute, Kolkata, where she works in the exciting and challenging domain of experimental nuclear physics. Our research focused on understanding the fission dynamics of heavy and superheavy nuclei, especially her complex interplay between fusion and quasi-fission, a major obstacle in the synthesis of new superheavy elements. We are truly proud to welcome Ajmira back among us as a speaker today. I now invite Ms. Ajmira Sultana to deliver a talk. The title of the talk is Fission of Heavy Elements and Superheavy Elements.
আলাদা করে খুলো গরমে খোলা আছে এটা ওই উপর মাঝখানে উপরে মাঝখানে আপনি স্ক্রিনের মধ্যে নিচে নিচে হ্যাঁ
Good afternoon, everyone. First of all, thank you for the nice introduction. And today I will talk about fission of heavy element and super heavy element. In this presentation, I will be focused on fission dynamics and application of fissions in our real life. So at first, I will talk about the discovery of nuclear fission. Otto Hahn was the main sole recipient for the discovery of Nobel Prize for the discovery of nuclear fission. Nuclear fission is a process where a heavy element breaks into two light fragments. And after the discovery of nuclear fission about 80 years ago has fascinated science as well as history of mankind. And at that time, Otto Hahn and Lise worked at Berlin and they bombarded neutron on uranium and they expect to form a heavier element with atomic number greater than uranium. But and this path is shown by the Fermi and their chemical analysis of this result shows that there is an element which is lighter than uranium and mass with lighter than uranium and the atomic number. The elements are krypton or barium. And for this work, Otto Hahn received Nobel Prize at 1939 and Lise works with her nephew for what's the amount of energy released in these reactions and they calculate the amount of energy released in this reaction about 200 mega volt and they publish their work in a major paper. And this is the illustration of fission. When a thermal neutron bombard on uranium, then it will produce 236 uranium in the excited state. Now, this is the excited nuclei. This is the excited nuclei. That's why it may undergo through beta decay. But the experimental result was surprising. They observed that it will not it will not go through beta decay. It breaks into lighter element like barium or krypton. And this is the and along with three neutrons. And this is the chain reactions for the nuclear fissions. And nowadays in movies like Oppenheimer also shows that how nuclear fissions in impact in political region also. And this is the amount of energy emit during after the nuclear fission. When we bombard neutron and uranium, then it produces krypton and barium with three neutrons. And if someone want to calculate the amount of energy released in this nuclear reactions, it's about going to 200 mega electrovolt. And this is the used energy. Now the point is that nowadays most of the electric power is generated using thermal power. If we use nuclear power, then it will beneficial for us. Now in this slide, I will show you what are the benefits of nuclear power over thermal power. Can you imagine in our really in our real life we need per day we need about 1,000 megawatt electricity. To produce this electricity, we need like 2.5 tons of coal, and which produce around 27,000 tons of carbon dioxide. But if we use uranium, it around 3 kg required per day, and it will and this energy is purely clean energy, and so this is not produce any harmful gas like carbon dioxide anything. This is harmful for our society. So nuclear power is more uh, clean energy than thermal power, and this is the main work of nuclear fission, and this is the main goal of fusion nuclear fission process. And why its discovery of nuclear fission is a very good example how curiosity driven basic research can lead to totally unpredictable and discovery of immense benefit to the society. And nuclear fission reaction is the mainly heart of any nuclear reactor. Nuclear reactor is the device which can produce nuclear power. So nowadays, nuclear fission reaction is important because not only for nuclear reactor, it is important to know the knowledge of mass and charge distribution of the fission residue are important for nuclear managing or nuclear waste management. And that's why it's important to know the fission dynamics or fission of heavy elements. And this is the block diagram of nuclear power plant. And inside the reactor, there is a inside the reactor, the fission process happen and fission produce heat. Like in earlier slide, I mentioned about 200 mega electrovolt heat will produce. So this heat uh, generates the steam from the water, and this this steam turns the turbine and which spins the generator, and then which produce electricity. And this is the nuclear reactor at BRC Bhabha Atomic Research Center. And this is not a power reactor. This is a research reactor. Like because in this reactor they provide neutron beam for research purpose for like material science or nuclear science research. But in India, we currently have 24 reactors, which is power reactor, and which produce electricity with 8 gigawatt capacity. But in the Union budget, 2025 to 26, the target is 7,100 gigawatt nuclear capacity by 2047. But this now I'm going to the next part of my second part of my presentation. This is mainly based on the formation of super heavy nuclear. Why super heavy nuclear formation is difficult? What are the challenges to form super heavy elements? First of all, super heavy element is the element which atomic number is greater than 104, and the heavy element is the element which atomic number less than 104. So this is the binding energy expression, and first term, as we know, this is the volume energy term. second term is the surface energy, and so on. So in nuclear fission, according to the liquid drop model, the nucleus becomes unstable or breaks into parts when surface a Coulomb energy term greater than surface energy term. So nucleus breaks into two parts. So the ratio of Coulomb term to surface term defined as a facility parameter, and this parameter decide the barrier of the valley. Like this is the expression of the barrier. If barrier tends to zero, that it means the composite system immediately breaks into two parts. If we calculate the facility parameter for Z equal to 104, then the facility parameter equal to 1. So fission barrier tends to 0, and it implies that the elements with atomic number Z equal to 10, it will break into two parts immediately. But in periodic table, we saw that there is a many element with atomic number Z equal to 10. There is a many element after Z equal to 104. So how this element exists? So this is because of cell effect. Now this is the periodic table, and all we know in the periodic table the last element is oxidation. But is there an end to the periodic table, or how can we form the super heavy elements? This is the challenge. How can we form this super heavy element, and which type of target and projectile can fuse to form a super heavy elements? And this is the experimental setup at Dubna, where the element organization discovered. And this is the experimental setup. This is the experimental chamber at Dubna. And this is the neutron number versus proton number. If you look into this, then you may see that this is the neutron stability line, but the super heavy elements lies in this region where the theoretical calculations they predict that there is a many elements with atomic number 120 and 126, but still experimentally it is not possible to produce because of because of less cross section, less fusion cross section. So how C or super heavy element is related with fission? So super heavy elements, like when we fuse target and projectile, then it's form a composite system, and it's called compound nucleus. Compound nucleus may under when target and projectile fuse, they form compound nucleus. Compound nucleus may go through this path or this path. If they go through this path, then we land up with evaporation residue or super heavy elements. So when target and projectile fuse, the composite system formed. This composite system breaks into two parts without equilibration of or decrease of freedom, like mass, energy, and by Z. And this nuclei go through this path, and this process is called quasi-fission. So quasi-fission is the main hindrance to the formation of super heavy elements. That's why it is important to know the interstandard parameter. What are the mass and energy, and what are the barriers, and what are the magicity of the interstandard parameter, like target and projectiles, mass and charge, etc. And if the system survive, componently survive, then its equilibrium all decrease of freedom, and it emits some light particle like alpha, neutron, proton, then it's land up with evaporation residue, and it is the super heavy elements. So now, first question is that then how we can fuse two nuclei, because both are positive charge. So there is a Coulomb repulsion. So to overcome this Coulomb repulsion, we need high energy charge particle. We need high energy charge particle. And how can I get high energy charge particle? And for this, we need a device called accelerator, cyclotron. Cyclotron is a charge particle accelerator device which can accelerate the charge particle. So, like charge particle like proton, neutron, proton, deuterons, oxygen, neon. And so cyclotron is used to study the thinnest particle like nucleus by which our universe is made of. Actually, a cyclotron can produce energetic charge particle
the mass an atom or nuclei to see what is inside it and to study their properties. And cyclotron, this is the block diagram of cyclotron. Cyclotron basically consists of two Ds, two Ds, and this is electrodes consist of two Ds. This is electrodes and connect to RF oscillator, and these are placed between the magnet. So the accelerating electric field reverses just at the time the particle finish their half cycle. So the polarity of these are synchronized with the velocity of charged particle. After that, it repeats the path several times, and they come out their exit port at high energy, and then it's go to the target. And this is the typical trajectory of the charged particle inside the disk. And from the principle of operation, so centripetal force equal to Lorentz force. So from that we can calculate the kinetic energy of the particle. So here you can see that the kinetic energy of this particle is directly proportional to R square, radius of the beam. So with increasing the radius of the beam, we can increase the energy of the charged particle. And this is used for nuclear experiment. And at BCC, we have three cyclotron, and one at BCC we have three cyclotron. One is K130 room temperature cyclotron. This is K130 room temperature cyclotron, and this is the real experiment. This is the scattering chamber where real experiment happen, and inside that there is a gas detector, and this is the gas detector. This gas detector also developed at our BCC, that's our institute. And this is the another cyclotron, K500 cyclotron, and this is the scattering chamber at K500 cyclotron, and this is the detector mounted inside the scattering chamber. And this is mainly gas detector because we are interested interested in fission fragments event detection. So if we this is the comparison between two cyclotron at K130 cyclotron, magnetic field 2 Tesla, around 2 Tesla, and superconducting cyclotron magnetic field around 4 to 5 Tesla, and their mainly K130 cyclotron provides low energy beams and light charge particles beam like alpha, deuterium, and proton, nitrogen, and oxygen. But superconducting cyclotron provide us high energy beam like 10 to 20 MeV per neutron beam, and beam like neon, oxygen, neon, krypton, and argon, and this one. And there is another cyclotron. This is medical cyclotron, and this medical cyclotron mainly provide as a isotope. This is used for cancer cancer treatment purpose, and this is the systematic of experimental setup. So so in experiment, in experiment there is a we get beam on cyclotron, and this beam hit on the target, then it produces a compound nucleus, and then it's weaker light charge particle or heavy charge particle. Currently, I'm interested with heavy charge particle. That's why we used gas detector to detect the fission fragment, because we have to detect these fragments. So this is the gas detector, and using this detector, we detect the fission fragment, and this is the charge particle array, and this is used for light charge particle detection like alpha, hydrogen, neon, this type of particle. And these detectors are placed at folding angle, the angle between the fission fragments. So from the experiment, what are the things we can measure and learn from that? We can get the charge and mass of the particle, tell us what the reaction was and what was made, and we can get energy and angle of the emitted particles, and that can be used to determine the Q value and excitation energy of the residual nuclei or source. The shape of angular distribution can also tell us about the reaction mechanism and properties of this residual nuclei. And we can also measure the cross section of different type of reaction. There is elastic, inelastic, and deep inelastic also. And this is the details of our MWPC gas detector, which is developed at our lab. So this is the gas detector. It consists of five planes. There is two cathode plane, and there is one anode plane, and there is one X plane, and another one Y plane. So cathode plane gives us information about the energy loss of the fragment. And anode plane gives us the time of flight of the fragments, and X and Y gives us the position of the fragments. So from that, we can calculate the mass of the fragment which we detect using MWPC gas detector, multi-wire professional gas detector. So at first we get position signal from we get the position signal X and Y. From that we convert into spherical polar coordinate theta and phi. And from time signal we get velocity. And from that we can calculate the mass of the fragment. And this is the typical relation between mass and velocity and time of flight of the fission fragment. Here, P1, P2 is the time of flight of the fission fragment, and MCL is the mass of the compound nucleus. D1, D2 is the flight path of the fragments, and P1, P2 is the momentum of the fragments. And this is the typical mass distribution of the fission fragment. If we bombard neon on thallium, then it will produce 25 platinum, and we produce the compound nucleus at higher excitation energy. That's why the composite system breaks into two parts symmetrically. That's why its mass distribution looks a single Gaussian distribution. But in case of alpha on gold, it will produce 201 thallium. But in that case, excitation energy is not high enough. That's why the composite system is not break symmetrically. It's break asymmetrically. That's why the mass distributions becomes asymmetric. And this will thank you. As about the nuclear reactors and detectors, I want to know about your experience on working on detectors as cyclotron as we only learned in the BSc. So I want to know how was your experience on working on the detector or the detectors? This detector developed at BCC, and so I can fabricate this detector by itself. And during experiment, we are also participating in the experiment, and we can set up all detectors and everything. Electrical, like experimental setup, electronics, everything done by itself. Can you help to show this detector? Yes, ma'am. So if you are interested, you can contact us, or we can make a group. Yes, যদি কেউ ইন্টারেস্টেড থাকে ম্যাম, যদি কেউ ইন্টারেস্টেড থাকে তাহলে আমাদের বিএসসিসি তে পাবলিক অ্যাওয়ারনেস সেল আছে, তো অনলাইনে ওয়েবসাইটে বিএসসিসি তে রেজিস্টার করলে সেখানে আপনাকে আমাদের যা ফেসিলিটি আছে সমস্ত কিছু দেখা হয়, মানে অ্যাক্সিলারেটর, ডিটেক্টর সব কিছু। কারণ এই ডিটেক্টর গুলো আমরা নিজেরা ল্যাবে ডেভেলপ করেছি, ফেব্রিকেট করেছি। আর সাইক্লোট্রন যেমন K500 সাইক্লোট্রন, এটা তো ফার্স্ট মানে এত হাই এনার্জি বিম ফার্স্ট টাইম ইন্ডিয়াতে এই সাইক্লোট্রনটা, তো ফার্স্ট মানে ইউজার হচ্ছে আমরা। তো এখান থেকে আমাদের 3-4টা পাবলিকেশনও হয়ে গেছে। তো কি সাইক্লোট্রন তো অনেক দিনই বিএসসিসি তে। না ম্যাম, ওটা হচ্ছে K130 সাইক্লোট্রন, রুম টেম্পারেচার সাইক্লোট্রন। আর যেটা আমি বলছি এটা হচ্ছে সুপার কন্ডাক্টিং সাইক্লোট্রন। আচ্ছা, সুপার। এই সুপার রুম টেম্পারেচার সাইক্লোট্রনে মেইনলি আমরা 4 to 5 MeV per nucleon beam পেতাম, কিন্তু সুপার কন্ডাক্টিং সাইক্লোট্রন হচ্ছে আপনার হাই এনার্জি বিম দেবে, লাইক আপনার 10 to 25 MeV per nucleon, মানে অনেক হাই এনার্জি বিম দেবে। তো আর সুপার কন্ডাক্টিং সাইক্লোট্রনে লাইক আমরা আর্গন, ক্রিপ্টন এই বিম গুলো পেতে পারি, কিন্তু আমাদের আরটিসিতে যেটা ওখানে শুধু আর তারপরে প্রোটন, নাইট্রোজেন, অক্সিজেন এই বিম গুলোই অ্যাফেক্টেড এবং লো ওয়াটেজ। শুধু গ্যাস ডিটেক্টর নয়, ওইখানে মানে আমার কাজটা যেহেতু থিসিস এর ওয়ার্কটা হচ্ছে মেইনলি ফিশন ফ্র্যাগমেন্ট ডিটেক্ট করা, আর ফিশন ফ্র্যাগমেন্ট ডিটেকশনের জন্য আমরা গ্যাস ডিটেক্টর ইউজ করি। কিন্তু অন্য ডিটেক্টর লাইক নিউট্রন ডিটেক্টর, তারপরে গামা ডিটেক্টর, এই সমস্ত কাজগুলো আমাদের করতে হয়। তো সমস্ত কিছুই ম্যাক্সিমাম ডিটেক্টর ইনস্টিটিউটে ডেভেলপ করা হয়। তো সেই মানে ফেসিলিটি গুলো বাইরের লোক মানে চাইলে কেউ দিয়ে রিসার্চ করতে পারে। আচ্ছা, তো প্যাক হচ্ছে পাবলিক অ্যাওয়ারনেস সেল, সেই তার মাধ্যমে রেজিস্ট্রেশন করতে হয়। বিভিন্ন কলেজ স্টুডেন্টরা ভিজিট করতে আসে, আমরা তাদেরকে ভিজিট করা। আমরা কোথাও যাইনি। আর আমরা ভেবেছিলাম কিন্তু হয়নি। হ্যাঁ, মানে আমাদের এখন যারা কলেজ স্টুডেন্ট, মানে যখন আমি গ্রাজুয়েশনে পড়তাম তখন আমার ডিটেক্টর সম্বন্ধিত আইডিয়া ছিল না। হ্যাঁ, তো ডিটেক্টর কি সাইক্লোট্রন ঠিক আছে পড়ছি, কিন্তু থিওরি আর রিয়েল এর মধ্যে অনেকটা ডিফারেন্স। তো যদি কলেজ স্টুডেন্টরা যায় তাহলে তারা অনেকটা আইডিয়া পাবে যে ডিটেক্টর কিভাবে কাজ করে বা ডিটেক্টর কি করে ডেভেলপ করছে, সাইক্লোট্রনের কিভাবে কাজ করছে। তো খুবই মানে তাদের জন্য যদি ভিজিট করেন আর এটা একটা মাথায় থাকবে।
Thank you, Ashmira, for your insightful and illustrative presentation. We wish you continued success in your PhD and in all your future scientific contribution. Next, we shall begin our cultural program. Before that, I would like to hand over the mic to Dipti Banerjee for the vote of thanks. Yes, Sunda. ঠিক আছে, সুমন বন্দ্যোপাধ্যায় উইল গিভ ভোট অফ থ্যাঙ্কস। তাই তো ঠিক বললেন। তারপর কালচার প্রোগ্রাম। দু মিনিট তো সবার একটা ছবি দিয়ে সবার থাকুন না, হয়ে যাবে। 2 মিনিট না, সময় থাকবো, দাও তখন। হ্যাঁ ঠিক আছে, ভোট অফ থ্যাঙ্কস বলতে সাধারণত আমরা সেমিনারের শেষে দিয়ে থাকি। তো আমাদের এইখানে দুটো ভাগ হয়ে গেছিল, যা বক্তব্য রেখেছেন সাধারণভাবে ভোট অফ থ্যাঙ্কসের সময় একটি বক্তব্য সম্বন্ধে আয়োজন বলতে হয়। সত্যি কথা বলতে কি, আমি অন্তরের বক্তব্য একটুখানি শুনতে পেয়েছি, আর একটা পুরোটাই শুনলাম ই এবং সি, আর ওনার খানিকটা শুনতে পেরেছি। তো একটা জিনিস যেটা হয়েছে, অদ্ভুতভাবে অন্তরের এবং অন্যান্য কাজের একটা বেশ যোগসূত্র হয়েছিল। তারপরে পারস্পরিক আলোচনা শুনতে ভালো লাগছিল, আমি যেতে শেষ দিতে শুনলাম। তো আমাদের অনেকদিন নানা রকম প্রোগ্রাম হচ্ছিল, অনেকবারই ভাবা হয়েছে অন্যান্য ডিপার্টমেন্ট তারা এরকম উইকলি বা মান্থলি একটা লেকচার আয়োজন করে, আমাদের নানাভাবে করে উঠতে পারেনি। এটাই না, এটা একটা শুরু হলো, একটা দারুণ উদ্যোগ। তো এইভাবে আমরা আপাতত যারা এলেন এই এলেন এবং এলেন না, সবাইকে এমনি একটা ধন্যবাদ দিয়ে আপাতত এই অংশটা শেষ করতে চাই। কারণ যারা কালচারাল কাজ করে তারা একটু বিঘ্ন হয়ে আছে, অনেক প্রোগ্রাম রয়েছে, তারা সেই কাজটা শেষ করবে। তো সেইটা সেই জন্য আমরা এখানে সবাইকে সবাইকে ধন্যবাদ জানিয়ে এবং ভবিষ্যতে আরো এরকম প্রোগ্রাম করার আশা রাখি। সবাইকে ধন্যবাদ।
ছবিতে এইটা বন্ধ করে দেবো, হয়ে গেছে, বন্ধ করে
যাই বলুন কিচ্ছু খাবো না আচ্ছা বলবো তো ওদের সঙ্গে
বলে জিজ্ঞাসা করে তোমার এই প্রোগ্রাম কি লাইভ হবে?
লাইভ কেন লাইভ করলে অসুবিধা আছে কিছুটা তো হয়েছে
আমাদেরকে সকালবেলা করার
ও তাহলে এটা বন্ধ করে দেবো।